Okay, so let's continue now with the third part of this presentation, which is entitled Control of Currents in Rotating Reference Frame, also called DQ control. And in this case, we will cancel the coupling terms. We will see now what do we mean with this cancellation of coupling terms. So the general control block diagram is this one represented here. From the left, as usual, we have the D and Q current references. Then we have the actual currents, the DQ component currents, that have been transformed into the DQ reference frame from the alpha beta reference frame. In order to do this transformation, we need the theta angle, that as before, we need a PLL that synchronize with alpha and beta voltage from the grid. In this case, we have simplified or neglected this element, and we suppose that we have the theta angle ideally. So from here, we calculate the error, and in this case, we will use PI controllers in DQ reference frame, and these outputs of these PI controllers after the outputs, we will cancel the coupling terms that later we will see where are they coming from. And finally, we have the D and Q component voltage references that again, by means of the theta angle, we need to change the reference frame into alpha beta, and here again we have the typical feed-forward term of the alpha and beta voltages from the grid. So these alpha beta voltage references, or the voltage provided by the power electronic converter, are applied into the two electrical circuits in alpha beta as before, and here in Laplace domain we will use the PI regulator that is composed by this equation, and we have here two gains, proportional and integral gains. Just keep in mind that here, as before, the current references are in DQ domain, and most part of the control are also in DQ. So at the steady state, we'll operate with DC currents and voltages. So the actual errors are calculated from the D and Q currents in constant, they are DC. These terms are also DC. And finally, with these transformations, we generate, and the theta angle obviously, we generate the actual or real voltage of the converters, which are sinusoidal. Obviously, the current measurements are in alpha beta or are sinusoidal. So this part is sinusoidal, while the control loops are made in DC. So the mathematical model in alpha beta can be transformed in something equivalent in the DQ reference frame. So if we have mathematically these time domain expressions for these two equivalent electrical circuits, in DQ reference frame, we can obtain these other equivalent time domain expressions, which are very similar, but at the steady state, these are constant current and voltages, while here we have sinusoidal currents and voltages. And here appeared these two new terms that we cannot find their correspondence in the alpha beta model, these two new terms, which are the coupling terms. In the electrical circuit, equivalent circuits, they can be represented as two voltages that depend on the current of the other circuit. So this Q current affects to the D circuit, while this D current affects to this Q circuit. So by doing the analysis in DQ reference frame, the previously represented control of the current in the rotating reference frame, the DQ control generates the voltage references in the DQ reference frame. So by eliminating this part from the control, well, it is in the control, but by equalizing these two voltages into here, in these two equivalent electrical circuits in DQ, we can obtain from here the control expressions, and we equalize to the power circuit with these two other terms. So developing these two expressions and applying the Laplace transform, we can obtain these two more compact equations. And if we rearrange the terms in transfer function form, we can obtain these transfer functions, which have a denominator of second order and a numerator of first order, 1, 0, and 2 poles. And for D and Q currents, we have the same transfer functions. So if we equalize the denominator to the canonical expressions, such in here, and we make equal this value to this value and this value to this value, we can obtain some analytical equations for the gains of the PA regulator in function of the damping and omega n, the natural frequency that we can obtain at the closed loop. So depending the damping that we want to obtain at the output current and the natural frequency, we can choose by these two mathematical deterministic expressions the gains of the PA regulators. So the pole zero map of this mathematical model in DQ is very simple. We have here these two poles, and here I have chosen one damping of 1.01, if I'm not wrong. So therefore we have two real poles, but they are different, but they are quite close from each other. And here we obtain the zero. And the numerical values for the resistance and for the inductance of the filter are the same as the ones that we have used in the previous control, in the alpha beta control. So if we substitute step inputs at both current references and we substitute them at the transfer function, we obtain the output currents for the D and Q components, and we see that we have two different terms, one depending on each, and they are decoupled, Here, only the D component current reference affects to the D component current, and only Q reference affect to the Q current, output current. And if we deduce the time domain expressions for these step inputs, we obtain something quite complex, maybe in appearance, but it's simple in a sense or in nature. Here we have the D current in time domain. Here we have one exponential term multiplied by this sinusoidal term. Here we have the constant term, which is the steady state term, because this term will be zero, and because we have also another term, which is the multiplication of a sinusoidal term and another exponential term. So these two terms are the natural response or the transient response, and this term is the steady state response. And something very similar, we obtain a totally equivalent, we obtain for Q current. These two terms, which are the natural response, and this is the steady state response. Okay, so giving numbers, and I have given the same numbers as in the previous control, in the alpha beta control, in order to be to have consistency, sorry. We have the step inputs at D component and Q components, such in here. This is given in the pole zero map, or this is produced due to the presence of these two real poles here, and this zero here. It's seen in the transfer function. And the body diagram, this is the amplitude, and this is the phase shift. If we apply here, for instance, sinusoidal inputs. So these three domains, the step response in time domain, the pole zero map, and the bode plot for the frequency response are often very useful in order to do analysis of the controls that we are applying or designing. So continuing with the analysis, let's go back again to the DQ control with cancellation of the coupling terms. But now we are going to derive the mathematical model in alpha beta reference frame. In the previous slides, we have developed in DQ frame, and now the objective is to do the same, to obtain the mathematical expressions, but in alpha beta. So if we develop the time domain expressions of this control, we can obtain for alpha voltage of the converter this equation, and for beta voltage of the converter we obtain this other expression. And again we have here the convolution product in these two expressions, and also the time product in both expressions. So now if we just further develop this expression by substituting ID, which is equal to this, here IQ, which is equal to this, and the same here, IQ is here, and ID is here. However, we do the same in the other expression. ID is equal to all this, and IQ is equal to all this. And we should do the same in IQ and ID in these two expressions, but I haven't done it because the expressions, the remaining or the obtained expressions or equations will be quite large to show here. So if we do the development, I'm not doing it here in this presentation because it's quite large and it would take quite a lot of time. It is done in the book from which I am presenting all this. If we do this development, we can finally obtain in Laplace domain or by applying the Laplace transformation in S domain, these two expressions for alpha voltage and for beta voltage of these control strategies. They are quite similar to, if you remember, to the alpha beta control, but they are not exactly the same. There are some similarities, but they are not exactly the same. Obviously, they shouldn't be the same because they are different controls. So they are similar, but not 100% the same. So here we have one term multiplying to the alpha current. Here we have the coupling, because beta current is also affecting to the alpha voltage. And then here we have the two terms for the current references. And finally here we have the feed-forward voltage term. And something very similar, totally equivalent, we have in beta and in alpha. This term is equal to this term is equal to this term is equal to this term, and this term is equal to this term. So there are some cross symmetries in these two voltage equations. So if we continue with the analysis, and as we did before, this is for the control, the equation that we obtained in Laplace domain for the control. And if we combine it with the power circuits in both components, alpha beta, we bring back again the previously derived voltage and current equations for the power circuit. And if we combine with the control, with these two equations, after several developments, we obtain the closed loop transfer functions for the two currents, alpha and beta, after having substituted in both D and Q currents references the steps. So here we see again that we obtained at the denominator this third order equation that depends on the resistance and inductance of the filter, the frequency of the grid, and the gains Kp and Ki of the, in this case, PA regulator. Here we have one term multiplying the ID, current reference, and the same term, if I'm not wrong, crossed, we have in the other current, but multiplying the IQ reference. Here we have another term multiplying the Q reference current, and here the equivalent one in the other current. And here we have the coupling. So these are the obtained current expressions, current transfer functions, after developing or after obtaining the closed loop. This could be represented in a block diagram, such in here, and something similar that we have done before with alpha beta control, but in this case is more complex, is more coupled. This gain or this element will be this one, this element will be this one, this element for the crossing will be this one. Here we have this term, here we have this term, and in here is this term. Okay, so the alpha and beta output currents depends on the D and Q current references, and there is some coupling between the two loads. We can further develop these expressions in order to try to eliminate this coupling. So if we represent these equivalent expressions in this more compact form, and after some developments, we can obtain these final and quite useful expressions, which are transfer functions, in this case decoupled. So the alpha currents depends on the D currents and on the Q currents, and this transfer function, this element and these elements, is in some way the combination of these all elements. And something equivalent we can obtain for beta current, something decoupled from D and Q current references. So now we can do a very similar analysis by using these quite useful expressions as we did with the alpha beta control, because we have obtained the equations which are decoupled. So only focusing on alpha current, because the other one is totally equivalent, if we have this term, which is, if I'm not wrong, this term, the one multiplying to D current reference, this is a 6th-order transfer function with 6 poles and 5 zeros. By using a symbolic toolbox, for instance in MATLAB, or using any other program, computer, we can derive that these gains multiplying the S at the numerator and the denominator can be represented by mathematically, analytically, by these 7 and 5 expressions. And for the other term, this other term, the one multiplied by Q, current reference, we have the same denominator, therefore the same poles, and the zeros are rather different from the other expression, but we can also have the equivalent expressions. So by using MATLAB again, for instance, toolboxes, you can obtain the pole zero map in the alpha beta frame for the alpha current only. This is what is represented here. Sorry. Sorry. And here, if we realize we have 2 imaginary poles, again at 50 Hz, and here we have 2 complex conjugate poles, which are the 6 poles of these 2 denominators. So these 6 poles give us 2 poles at the imaginary axis, which are the steady state response, and these 2 complex conjugate poles are the transient response, the natural response. And if we compare it with the pole zero map in the DQ frame that we have made in the previous slides in this video or in this presentation, we see the correspondence between the DQ frame poles and the alpha beta poles, only focusing on the poles. So here we have poles more or less real at 200, a little bit less of 300 real parts, and these are the same real parts, more or less 200 and more or less 300. Same real parts in DQ frame and in alpha beta frame. However, here we have the imaginary part at 50 Hz and the frequency of the grid, because we are now in the alpha beta frame. And for the steady state here is DC, therefore we don't have a pole in the imaginary part, but in order to create the steady state, the fourth response, we have these two poles. So now if we substitute here directly the step response, the step inputs in alpha current for both, we develop with the previously obtained expressions, and we obtain the time domain current, the time domain equation from here after substitute the step inputs, and we realize that we obtain again two terms, one multiplied by the amplitude of the step at the D reference and the other one for the Q reference amplitude. They both terms are equivalent, and here we have, yes, here we have one exponential term, another exponential term that will be extinguished at the steady state, so these terms will be zero at the steady state. Therefore, these are the natural response or the transient response, and these two terms are cosinusoidal terms, are the steady state response. So by using the function residue from MATLAB, for instance, we can obtain the numerical expressions, the numerical expressions for these all gains. They will be the values. And again, if we validate these mathematical expressions that we have obtained with this mathematical development, with, for instance, the implementation of the block diagrams of the control in DQ frame, and here we have the filter and the grid, the power circuit. So this is the control, these are the PA controllers, these are the cancellation of the coupling terms, and these are the reference frame transformation. This is the detangle, and this is the power circuit, one for alpha and the other one for beta. And if we compare with the developed analytical expressions, and we superpose again, and we put here one step input of 1 amps for each input, current references, we obtain here the alpha beta voltages of the converter, and we have here the alpha beta currents through the system, and here we can also represent the natural response only in alpha. So here we have to highlight that both analytical or mathematical model and the Simulink blocks provide us the same response. Therefore, we have validated, we can say that we have validated the previously derived mathematical expressions. Okay, so let's come back again to the DQ control block diagram, and here we have the power circuit, and now we are going to do, as we did before, the analysis when we have at the current references sinusoidal and cosinusoidal inputs. So for the D current reference, we will use a sinusoidal input. Here we have the Laplace transform, and for the Q current reference, we will use a cosinusoidal input, and here we have the Laplace transform for this one as well. If we do the same analysis as before, following the same procedure, deriving the equations of the control and the equations of the power circuit, applying the Laplace transform, equalizing and developing the terms, we can obtain these two expressions. Again, in the book, you have all the developments, which are probably quite long to be presented in this presentation. So we obtain something very equivalent as we obtained with the step inputs. Here we have for alpha current, here we have one component or one term multiplying for ID by ID, another term multiplying IQ current reference, and here we have the coupling, and something very similar for beta current. Here the main difference is that we have defined another 4 elements, D alpha, Q alpha, D beta, and Q beta, because the expressions obtained are more complex, so they need it. And these 4 terms, D, Q, and D, Q for alpha and beta, are these expressions, which are rather complex because the nature of the sinusoidal and sinusoidal inputs that we have used as current references. So, as we did before with the step inputs in this control, in this DQ control, if we try to solve this coupling, if we try to eliminate this dependency of beta current to alpha current and this dependency of beta current from alpha current, we can do the same process as we did before, put these expressions in a more compact form, and then after several developments we can obtain the couplet, actually the couplet transfer function expressions which relate the alpha current with D current reference and Q current reference, and something similar for beta currents. So they are totally equivalent expressions, but the only change are these terms compared with the step inputs. These are totally equivalent to step inputs. So if we obtain the pole zero map with these sinusoidal and cosinusoidal inputs, what we obtain is something quite equivalent to what we have obtained with the step inputs. If we focus on alpha only, we realize with this expression, this is for this, and this is for this, and they have the same poles, they have the same denominator. So if we focus only here, we realize that we have the steady state poles, the imaginary poles, so they don't have real part, so they don't distinguish during transient, therefore they are the steady state response at frequencies omega 1 plus omega and omega 1 minus omega. And here we have again 2 complex conjugate poles, which are the transient response because they have real poles. So they are extinguished at the steady state. So these are the transient response poles, and the same happens with this element, which is this element, imaginary poles and transient response poles, the same. However, here, due to the presence of this zero, the scale is totally different from here to here, but the poles are the same. And if we compare these poles, for instance, these ones, with the poles that we obtain for step inputs, we realize that the transient poles or the natural response poles are exactly the same here and here. Again, the scales are different, but we realize that they have same real parts and same imaginary part, which is again the frequency of the grid, which is in this case in radians per second 314 radians per second. So here you have the equivalence of the parallelism. So again, from those transfer function expressions, we can obtain the time domain expressions after substituting the sinusoidal and cosinusoidal inputs. And again, we have some, in this case, steady state terms at the beginning. And here we have the exponential terms, which are the terms that are going to make zero, are going to be zero at the steady state. Here multiplying to D current, and here multiplying to Q current. Again, these two terms for the steady state, and these two terms for the transient. If we analyze only this term, taking into consideration that we have put zero at the current reference of the Q component, which is this, we are doing this. Again, we can obtain the body diagram, and at the steady state, we realize that we obtain two currents. In this case, given these numbers, we have put it here 250 Hz, here we have 200 Hz, and here we have 300 Hz. At the steady state of amplitude, both they have same amplitude of 0.154 amperes. We obtain the same amplitude for both sinusoidal currents at the output. And this is well seen if we obtain the Bode diagram by using MATLAB, for instance, and we see that at both frequencies, this frequency, and this frequency, this frequency, and this frequency, that we obtain the same gain in decibels, which is these gains, 0.154 amps.